Yes, sir.
Okay, fine. So let us then begin today's session. So in the last class, we were seeing about Maxwell's bridge. Then we had completed Hayes bridge. And now we have to see what? We have to see your Anderson bridge. After that, we have few questions. So have we solved this question? Homework question? Did we try it once? Okay, it's okay. So when we will be seeing that, at that time we will see what is happening. Okay. So now let us start with Anderson bridge. So Anderson bridge, as I have told you, it is actually a bridge that is used for measurement of inductor having low quality factor. You can see. Okay. So I have written Anderson bridge is used for quality factor of a coil that is very low or less than 1. Okay. So basically in Anderson bridge, this part is unknown. This is unknown. Then what is this small r1? So this small r1 is basically kept in the circuit by default, so that if sometimes if we get coil which has quality factor greater than 1, so what we can do, we can increase this value of r1. Okay, so what it will do, it will actually reduce the quality factor of this coil, because with the help of Anderson bridge, what happens, we are going to see in a few moments that we are only able to measure low quality factor coil. So sometimes if we get a very good quality or a medium level coil having quality factor in the range like quality factor is equal to 2 or 3, something like this. So then if we want to measure this inductance, what we do, we increase this value of small r1 such that the quality factor decreases. Okay, so that we can measure the inductance with the help of your Anderson bridge. Is it clear? Any doubt? Did we understand why have we kept this small r1?
Yes, sir.
Okay, just a second. Okay, so now let us see the analysis of this bridge. So Anderson bridge is the only bridge which has 5 nodes. You can see there are 5 nodes present. This is node number 1, node number 2, node number 3, node number 4, and this is node number 5. So Anderson bridge is a bridge which has 5 nodes. Okay, so now how do we basically do the analysis over here? So now look very carefully. This part, okay, this part, this is basically a delta. Okay, this is basically a delta. What I can do, I can do delta to star transformation. Okay, delta to star transformation I can do very easily. So first see the analysis, then you can copy. Okay, so this is R, this is C. That means this will be J by omega C. Impedance will be, and this is R4. Okay, this is R4. So now let me draw the equivalent star network also. Okay, so what we can see, let this be X, this be Y, and this be Z. Okay, so value of X will be equal to what? It will be equal to R into minus J by omega C divided by R plus R4 minus J by omega C. Tell me, is this clear? Is it clear? So simply this is what, this is your star to delta, delta to star transformation I am doing, nothing else. Okay. Next, y will be equal to what? It will be equal to R into R4 divided by R plus R4 plus 1 by j omega c also you can write. Whichever way you feel comfortable, you can write that, okay? So let me write it as 1 by j omega c. So it is easier for you then. Okay. Z is equal to what? Z is equal to R4 into 1 by j omega c divided by R plus R4 plus 1 by j omega c. Okay. So this is what? This is my value of Z. Now let me assume what? Let P is equal to R plus R4 plus 1 by j omega c. Okay. So I have assumed that this P is equal to what? R plus R4 plus 1 by j omega c. So X I can write it as what? X I can rewrite it once again. Okay. Acha. So we have this much. Up to this point, any doubt? Any doubt? Fine. Acha, one thing I forgot to tell you that this R1 is actually known to us, okay? This is known because we are only setting this. If the quality factor of the coil is very low, we set the R1 approximately equal to 0. If the quality factor of this coil is high, we set a we set a value which actually brings the quality factor of this coil down to 1. Okay. What is happening to my tablet? I don't know exactly. Just a second, okay. Okay. So now let me redraw this diagram. See, I will be making changes in the same diagram. You have to make one more diagram. Okay. So basically, if you see, this is my X branch. This is Y. And this is Z. This is X. This is Y. This is Z. See, I am making changes in the same diagram. And what I am going to do, now I am going to erase this, or else it's okay. I will. Okay. So this was your figure 1. This is your Anderson bridge. This is figure 2. And this will be your figure 3. Now see, basically this is the converted delta to star. Now I am going to remove this part. Up to this point, is it clear? Tell me yes or no. See, up to this point, is it clear? Okay, so this is what? This is your figure 3. Now one more figure I will be drawing. So this is figure number 4. Now see what all changes happen. So I will be bringing this node over here, okay, at this point. See, so what will happen? I will be redrawing this. So look very carefully, or else it's okay. I will make one more diagram so that you guys can understand. Figure number 5. If you are understanding, it's okay. No need to make so many diagrams. It's okay. See, if I bring this point from here to here, what will happen? This R2 and Y, it is in series. So now I can write it as R2 plus Y. See, this X point is now over here. So now this will be what? This is your X. Okay. And this Z point means your Z impedance branch. It will be over here. Z. So this is your now fifth diagram. This is your modified Anderson bridge. Tell me, is it clear? The diagram, is it clear to you guys? Any doubt in this? Okay. So now what we have to do for the bridge to be balanced, we know the condition. Once again, Z1, let us assume this is Z. So let this be Z1, this be Z3, this be Z2, and this be Z4. So we know what? Z1 into Z4 should be equal to Z3 into Z2. So Z1, we have to write it over here. So I am writing in the next page. See, Z1 is equal to what? If you see R1 plus R1 plus J omega L1. This is your Z1. Okay. Into Z4. So Z4 is Z is equal to Z3. So Z3 is R3 into Z2. So Z2 is R2 plus Y. Now let us put the values of Z and Y. Okay. So R1 plus J omega L1. What is the value of Z? Z is this value is equal to R3 R2 plus Y. So what is Y? What is happening to my tablet? I don't know. See. Okay. So this is what? This is my Y. Now we know what? R1 plus J omega L1. This we can write as R4 by J omega C into P. This is basically P. I have assumed it to be P. And this will be R3 R2 into P, because this is also P. I am taking LCM. So this will be R into R4 divided by P. Okay. So P and P gets cancelled over here. So now we need to solve this basically. So can we solve it now? Tell me yes or no. Can we solve this? Solve. I will also keep on solving. I want you guys to solve this. Solve it. Into P. So P is plus R4 minus J by omega C plus R4 R3 into R. Okay. R4 L1 by C minus J R4 by omega C R1 plus R1 is equal to, okay, so this will be R3 into R2 R plus R4 plus R4 R3 into R minus J R3 R2 by omega C. Check if this is okay or not. If we are getting this or not. I might have made some mistake. Okay, but I'm sure I haven't. So just see if you are getting this or not. Check. See, this question, same exact question you will get. So it's not like this much calculation won't come. It might come in exam. Look. Okay. Same exact question. This is your gate question. Okay. I forgot to write the year. I think it's 2009 or 10. So you have to be very good at all these things. Okay. Tell me. Up to this point, is it clear? Are we getting this much calculation or not? Now we can equate the real part and imaginary part. So R4 L1 by C is equal to whatever this value is. So this is a big value. R2 R3 R plus R4 plus R3 into R4 into R, and this value is equal to this value. So R4 by omega C R1 plus R1 is equal to R3 R2 by omega C. So omega C gets cancelled. So you get what? You get R4 R1 plus R1 is equal to R3 into R2. Tell me, is it clear up to this point? Is it clear? Now even you can get what? You can get L1 also from here. So L1 will be equal to C by R4 into whatever this big value is. Okay, so this is L1, and you can even get R1 also. So R1 is equal to R3 into R2 by R4 minus R1. See if we are getting this or not. Are we getting this? अरे yes no बोलो जल्दी. Is it clear? So now which all are the parameters which we should vary over here? Can you tell me in Anderson bridge? See, both of this term R3 R2 is present in both of them, so I cannot select this. R4 is also present in both of them, but this R1, it is specifically present in this R1, it is not present over here, and this C is present in L1. Okay, so basically I can vary C and R1. So usually R1 and C are the variable parameters over here. This R1 is variable and this C is variable. So with the help of this two parameter, we usually balance the bridge or converge the bridge. Tell me, is it clear? Any doubt? So these two are the expression. Any doubt in this? Tell me. Did we understand? So note it down quickly if you haven't noted any point. So noted everything. So one thing to note is this, that your Anderson bridge is independent of frequency. First point. Anderson bridge is independent of frequency, not a function of frequency. So it is independent of frequency. Okay. Is it clear? So another thing, one more thing over here is that the circuit is complex. You can see quite complex. We had to do so much analysis. So circuit is little bit complex in Anderson bridge. One more thing is that we can even balance the bridge by doing what? By just varying this R1. Okay, we can balance the bridge by only varying R1, but if we want to calculate the quality factor of the coil, then we require to vary the C also. Okay, if we want to calculate the quality factor of the coil, then we need to vary C also. Okay, so here you can tell that this bridge is also very cheap because we don't require variable capacitance. If we just want to measure the value of your inductance in the coil, then only. Okay, so if you want to measure inductance, just with the help of R1 you can do, but if you want to measure the quality factor of the coil, then you need to vary C also. Okay, any doubt in this point? Any doubt? Okay, fine. So today you guys had network class, July batch. Okay, I saw actually from 5:50 to 7:50. Did you guys attend? Means only I think Shishir, Nitish, he has actually studied. Fine, good. So how many people are present in that class? Means in network only 2 people are present. Sorry, in MMT means in measurement. So how many people are present in your network class? 4 to 5. चलो कोई बात नहीं. It's okay. Those who want to seriously study, they will be present. Those who don't want to study, they won't be present. Okay. So next is what? Next we have is Owen's bridge. So Owen's bridge is basically used to find out what? It is used to find out your, we have already seen mu r. Okay. Magnetic permeability we actually find out over here. Okay. So here basically mu r of what? So mu r of this coil. Okay. So this is basically unknown. So how do we do the analysis? Analysis part is still the same. Okay, so I forgot to write, this is R2, this is C2. Okay, so analysis part is still the same. At balance condition, let this be Z1, this be Z3, this be Z2, and this be Z4. At balance condition, what will happen? Z1 into Z4 is equal to Z2 into Z3. So after this bridge, we are going to see few questions, okay? Because we are studying theory from 2 classes, so it's not good. We have to see some questions also. Okay, so Z1 is equal to what? R1 plus J omega L1, and Z4 is equal to 1 by J omega C4 is equal to Z2. So Z2 is R2 plus 1 by J omega C2 into Z3. So that is R3. Okay. So now what you can see, if I expand this to, so what I will be getting? So L1 by C4 minus J, this will be R1 by omega C4 is equal to R2 R3 minus R3 by omega C2. See if this is clear or not. Okay, is it clear? So very simple thing. This bridge is very simple to do analysis. Okay, so now what we can write, equating the real and imaginary part, L1 by C4 is equal to R2 into R3, and R1 by omega C4 is equal to R3 by omega C2. So omega omega cancel. Okay, so L1 is equal to R2 into R3 into C4, and R1 is equal to R3 into R1 divided by C2. Okay, so we have what? We have your L1 and R1. So what are the uncommon variables over here? Uncommon variable. So you can see in L1 we have C4. Okay, or we can even write over here, means uncommon is R1. Okay, so I should have
Sir,
asked this one. Bolo.
our second equation, it should be R1 equals to R3 into C4, right?
Which one? Second
Second
equation,
one.
this one.
No, no, for R1 we found that expression. For
This one.
R1. Yes, sir.
R1 is equal to R3. Okay, so this will be C4. Okay, C4. Okay. Okay. So now what are the uncommon parameters? So here both C4 is present, so it is not taken. So here R3 is also present. So here R2 is uncommon and here C2 is uncommon. Okay. So you can see basically I can vary these two parameters to do what? To balance the bridge or converge the bridge. Okay. Fine. So now quality factor. Quality factor. See, one thing I want to tell you, I can balance the bridge even also by keeping this C2 constant. Okay, I can balance it up to some extent. Up to some extent, not exactly, but near to balance condition I can do with the help of R2. But if I want to determine quality factor of this coil, I always need this C2 as variable. Why? Because quality factor I can always calculate only at the balance condition, not nearby condition to the balance condition. So these things need to be kept in your mind, that for calculating the quality factor, you need to vary both R2 and C2. Okay, you need to vary. So now if you want to calculate the quality factor, so quality factor of this coil is omega 1 L1 by R1. So omega L1 I have calculated, that is R2 R3 by C4, sorry, R2 R3 C4 divided by R3 C4 divided by C2, that means multiply by C2. So R3 R3 C4 C4 cancel. So this is omega R2 C2. So you can see, if I want to calculate the quality factor, then I need to vary both R2 and C2. Without varying both, I cannot do so. Okay. Quality factor can be determined by varying both R2 and C2, whereas the bridge I can nearly converge it by varying just R2 also. Okay. So tell me, is it clear? Is it clear? So this coil, Owen's bridge, usually this is also used for medium quality factor coil, that is quality factor having 1 to 10. Okay. So now we have to find out what? So look over here, we will be finding out mu or the value of inductance. So usually it is not asked. Okay. Usually it is not asked, but still we are going to see. Okay. So we know what? Magnetic flux is equal to inductance into current passing through the coil. Tell me, do we know this equation or not? Do we know this equation? Arey, what, we don't know this? This is basic EMT. This is another, means just like Ohm's law states that in a resistance, voltage is directly proportional to current when temperature is constant. Similarly, for inductance, your flux is directly proportional to the current flowing through the coil. Okay, coil or inductance, whatever you want to say. So if I remove this proportionality sign, so this is L, inductance of the coil. And similarly, if I remove this proportionality sign, it is resistance. Okay. Similarly, for capacitance, charge stored by the capacitor is directly proportional to the potential difference between the plate. If I remove this proportionality, so these are all form of Ohm's law only. Okay. Fine. So this is what? This is for a coil that has only one turn. This is for a coil that has one turn, n equal to 1. What if a coil has n turn? Then the number of flux will be also n phi times. Okay, this is for coil having n turns. Okay, for a coil having n turns. So then flux will be n phi. So this will be also equal to Li only. Now don't think here we are going to multiply with n. No, no. Okay, this is for a coil having n turns. So we have studied EMT or not? EMT. So this is basic EMT. Hurry. Shishir, Nitish, tell me. EMT is yet. Okay, so this much then you must be knowing. Okay. So now if I want to write magnetic field, okay, so that is flux per unit area is equal to magnetic field through this inductor. So that is what I have written. So let this be equation 1, this be equation 2. Okay. So phi I can write it as B into A. So put this over here. So you will be getting what? NBA is equal to Li. Okay. NBA is equal to Li. Okay. One more thing. Do we know this or not? Do we know this? What is this? Define. What is this? इतने देर से तो मैं बोल रहा हूं. Now you guys tell me what is this? Tell me quickly. What is this? See, you guys are just telling me yes sir, okay? Actually, you don't know what notations I am using. Okay, it's not very good that you guys are doing like this. See, if you don't know, it's okay. Just give me a minute. Why am I getting OTP? So till that time you tell me what is this? What is B? What is B? Yes, magnetic field या flux density. What is H? What is H? Magnetic field strength. Okay, very good. So magnetic field strength. So magnetic field is directly proportional to magnetic field strength. Now if I remove this proportionality sign, I get this mu, which is the magnetic permeability of the medium or space over here. So if I use this equation over here, so I can replace it in mu h a is equal to Li. Okay, so now if I want to calculate mu, so that will be Li divided by N HA. So already you can calculate the value of L from this place. Okay. I, you can also determine it, the current that is flowing through this arm at your balance condition. You will be already knowing because you know the value of R1, L1 and this source. So you can also calculate I. Number of turns of coil, it is also obviously written. Now field strength, how are you going to calculate field strength? Field strength, बताओ. अरे how are you going to calculate field strength? Means we are forgetting everything. From BH curve, भूल गए बताओ. From BH curve, we can calculate what? We can calculate the field strength. So we have forgotten everything actually. So do we remember this or not? Huh? Do we remember this? Hopefully now you might be remembering. So now even this is very difficult for me to draw, okay? So very difficult. It always confuses me. It's something like this, okay? But I am not able, always this thing actually creates a problem for me. It's a kind of S like this, but I am not able to draw. Okay, always this thing happens with me. So when I want to draw the BH curve and show the hysteresis, it actually creates a problem. Okay, wait. Now it's correct. So every time I try to remember this trick of drawing this and then I forget. So first I need to draw this and then means this is not the exact one. The straight line should pass from here. Actually this is also wrong. Wait, I will draw the correct one only. No, it's correct. Approximately it's correct now. चल जाएगा. So are we remembering the BH curve? 5th semester. So it's actually very difficult because I can't. Now it's correct. Okay, so this is the BH curve. Now do you remember? Tell me. So this is basically the red color one which I have drawn. It is actually for having your air core coil. Okay, air core coil, and this is the BH curve for your what? This is the BH curve for your material coil which has material in between. Tell me, is it clear? Any doubt? Doubt तो होगा ही, because we don't remember this BH curve. Okay, we don't remember anything. So please once go and study BH curve. It's okay, even if you don't remember, it's okay, it's fine. You are going to study it in your EMT. Okay, at that time please study. So this thing might not be asked to you in exam. Still I thought I will just discuss with you once. Okay, is it clear? Any doubt? Any doubt? Chalo. So next we have is a question. So tell me, what is the answer for this question? This was homework question. What is the answer?
So option C.
Option C for this one you are telling, and for this one? For this one? So we haven't solved. Chalo, first we will solve this one only. The figure shows a balanced AC bridge is excited by a voltage source of fixed frequency. Okay. The impedance of unknown arm Z is. So what is this unknown arm Z? So if nothing is given, consider this as R1, this as R2, L2, and this as R3. Okay. So now you can see what? If this bridge is balanced, it is given. So we know R1 into R3 is equal to Z into R2 plus J omega L2. So Z is equal to R1 into R3 divided by R2 plus J omega L2. So I can write it like 1 divided by R2 by R1 into R3 plus J omega L2 by R1 into R3. Okay. Tell me, is this clear or not? You are telling R and L in series. So there are two options. Okay. Someone said me C. Acha, C, I think Shishir told me now. Acha, for the next question, I think you are telling me A. Okay. Now, two things you need to remember. What is L by R? What is L by R? Time constant, you are telling me. Okay, time constant. And what is RC? What is RC? This is also time constant. Okay, that means these two quantities have the same unit, that is second. Okay, that is second. Now look at the transfer function of the Z. Okay, look at the transfer function of the Z. So is it like RL in series? Because if we have RL circuit in series, so it will be like R into J omega L divided by R plus J omega L. So this is J omega RL divided by R plus J omega L. Is it looking like this? No, it is not looking like this. So option A is wrong. Next is option B, R and C in series. So R and C in series, it looks something like this, but this is not looking like this. Once again, option B is wrong. Okay, so sorry, this was R and L in series. I have done R and L in parallel. So this is option D. Okay, I'm very sorry. So I read it wrong. Okay, so this is option B. So option A, if you check option A, that is R and L in series. So that also looks like this. Okay, so this transfer function, it is not even looking like this. So only option you are remaining is option C. And even if you want to check R and C in parallel, so that will be R into 1 by j omega C divided by 1 plus, sorry, R plus 1 by j omega C. So you can write it like R divided by 1 plus j omega RC. You can write it like this. You can do what? You can divide this R. So this will be 1 divided by 1 by R plus this will be j omega C. Whichever way you want to write, you can see that this looks quite similar. Okay, this looks quite similar. So that means what? That Z is basically what? This is R and C in parallel. Okay, R and C in parallel. What is 1 by T? Bhool means you guys are forgetting everything. Time constant for RL circuit, it is L by R. Time constant for RC circuit, it is RC, not 1 by RC. ऐसे होगा. Have we forgotten all these things or what? Okay, and directly also, if you didn't want to solve, this is basically Maxwell's bridge. Okay, Maxwell's bridge. But it's okay if you don't remember, no need for memorizing. This will take only what, 30 seconds to solve. Okay, if your network is very good, it will take you just 30 seconds to solve this question. So next, tell me, what about this one? Answers? Bolo.
In this previous question, as we told, that's a Maxwell bridge. So we can also say that if R and C are in series, then it's a Hayes bridge. So, uh, so are the B and C options? So we can assume both the options are correct.
You are telling me what? That R and C in series.
Yes, sir.
Okay.
For Hayes bridge.
Come to Hayes bridge. Okay, so this is Hayes bridge you are telling me. And you are telling me for Maxwell's bridge, you can write it like this. Okay, fine. Yeah, this is also okay. So what you are telling me is quite okay. Your question is quite valid. You are telling me, sir, this is Maxwell's bridge. You can even take it as Hayes bridge. Okay. So why can't I take Hayes bridge?
So since it has been given to us that it has been excited by a voltage source of fixed frequency, and we in the Maxwell bridge we have
Yes,
learned
yes,
that.
yes, 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 yes. Very good. Okay. Yes, very good. So this is very good. So Hayes bridge, if you go back in Hayes bridge, basically omega is variable. Whereas Maxwell bridge, it is independent of frequency. Okay, it is independent of frequency. So from this one, we can basically differentiate between Maxwell's and Hayes bridge. So very good. Okay. So who said this to me, Nitish or Shishir?
Shishir.
Okay, so very good, very good. Okay, so even I was not able to think you did this, so it's very good. Okay, so that is a very logical point that you have said to me. So very good. So this one now, tell me. So even the question which was asked by you, okay, by Nitish, I think Nitish asked. So that was also very good question, sir. Why are you telling this as Maxwell's bridge? Even it skipped my mind that yes, it can be Hayes bridge also, but it is given of fixed frequency, so it cannot be Hayes bridge. Okay. Chalo. So now tell me. So very good, both of you. So this shows that you guys are attending the session very good. Okay, carefully you are studying. Acha, chalo. So same once again. So what is given? A bridge circuit is shown in the figure below. Which one of the sequence given below is most suitable for balancing the bridge? Okay. So now here it is not said basically which parameters you need to balance. Okay, which parameters you need to balance. It is not said over here. So what are you going to do then? First, basically write the equation. So if you write over here, R1 plus G means, sorry, let this be Z1, this be Z3, Z2 and Z4. So Z1 into Z4 is equal to Z2 into Z3. So Z1 is equal to R plus JX1 and Z4 is R minus JX4 is equal to R2 into R3. So this we got. Okay, fine. So now if we open this, okay, so this was R1 and this was R4. So let us open this. So this will be R1 into R4 plus X1 X4 and over here plus J into, so this will be X1 R4 and from here it will be minus X4 R1 is equal to R2 into R3. Okay, fine. So this much we are getting. So now what we can write? R1 into R4 plus X1 into X4 is equal to R2 R3 and X1 R4 is equal to X4 So this equation, okay, this equation, even this bridge, it looks like what? It looks like Hayes bridge. But here you can see they haven't actually told us which are the variables present. So if you assume R1 and X1, sorry, R1 and X1 as unknown, and if you proceed over here, then you can see here R1 is present. Okay, R1 is present in one of the adjustments. So what you can do over here, see, look basically the uncommon terms. Okay, uncommon term. So you can see R4 is present in both. Okay, here R1, after R4 then it's R1. So R1 is also present in both. Okay, R4 is present in both, R1 is also present in both. So this cannot be the case. Next is R2. So if you check, R2 is present over here in this place, but R2 is not present over here. What about R3? R3 is present only over here and it is not present over here. So this also cannot be the case. Why? Because both the variables, it is just affecting my equation 1, I have no control over equation 2. Option B cannot be also the case. Then what it is? First adjust R2. So you can see R2 is present over here. Then adjust R4. So even this is present over here and here. Okay. So even this also cannot, wait a second, R2 and R4. First adjust R4 and R2. So this is quite complex. Is there some mistake in the options? Just give me a second. We are getting such an option. First adjust R4, then adjust R2. This is also present. R2, R4 is also present. First adjust R2, then adjust R3. So option B I can neglect because this is only affecting equation 1. Okay. First adjust R4, then adjust R1. Means all the three options. Is there some mistake in the options or what? First adjust R4, then adjust R1. Which one of the following sequence given below is the most suitable for balancing the bridge? Okay. So balancing the bridge. My main aim is to balance the bridge. That's it. Okay. Okay, so first adjust R4. Okay, so now we can do it. So we cannot solve this question like this. See, once again, let us start. So we got all these cases. Okay, we got all these cases. Now look, first adjust, they are telling what? First adjust R4, then adjust R1. So first adjust R4, then adjust R1. So you can see R4 and R1, both of them are present over here. Okay. So this can be one of the option. We don't know yet. Option B, first adjust R2, then adjust R3. So R2, R3, it is only present in this equation. It is not present over here. So directly we can neglect this. Next is first adjust R2, then adjust R4. So first adjust R2, then adjust R4. Okay. So this can also be the option. Okay. First adjust R2, then adjust R4. Next, what they are selling? They are telling us that first adjust R4, and then adjust R2. Okay. So here also we have R4 and then we are adjusting R2. Now see very carefully. When we are doing this one, option A, so we are doing what? We are manipulating this two simultaneously. Okay. And after that, we are setting this one. You can see first adjust R4, then you are adjusting R1. Okay. So R4 is present in both the equation and then you are manipulating. So at the moment you might think that this is quite confusing, but look at option D now. Option D. First adjust R4, okay, and then adjust R2. So here they are telling first you have to adjust this R4 and then you have to manipulate this R2. So what is the difference in this two? Can you guys tell me? Can you guys tell me? that we are trying, first we are manipulating in both these two cases, A and D, we are manipulating both R4 only, and then we are manipulating R1. Okay. But in this case, when we are doing option number D, at this time we are manipulating R4, okay, and then we are manipulating R2, which is present only in this equation. It is not present over here. Previously, you can see we were manipulating R4 and then we were manipulating R1, which is present in both the equation. So once again, after setting, I am disturbing both the equation. Are you getting the point? Whereas in option D, once I am setting R4, I am just disturbing R2, which is present in this equation. I am nowhere disturbing this equation because R4 has already been set. I am disturbing R2. Are you getting the point? Tell me. See, is it clear? Shishir, is it clear to you?
Yes, sir.
I don't think it's clear yet. See, once again, let me make this thing proper. R1, R4. It's okay. Even if you don't understand, you can let me know. Sir, I haven't understood. And here it is X1, R4 is equal to X4, R1. See, now try to understand. See, already I have eliminated option B. Because with the help of B, I can just do what? I can just manipulate one of the equations only. Okay, so this is equation 1, this is equation 2, this is also equation 1, this is equation 2, this is option A, this is option D. In option A, what I am doing, first I am adjusting R4. So my first case is to adjust R4. So this is first. So I have set R4, I took the bridge near about to your balance condition. It is not perfectly balanced. Okay. So I have set this to. Now next is what? I am adjusting R1. So if you see, my next step is to adjust R1. So when I adjust R1, this is second, this is also second. So I am once again disturbing both the equation. But now look at option number D. Option D is telling first adjust R4. So first you need to adjust R4. So this will cause both the equations to change. Okay. I will take the bridge near to balance. It will not be exactly balanced. And in the next case, adjust R2. So when I adjust R2, you can see I am just manipulating this equation. I am not disturbing this one in any way. Whereas over here, I am disturbing both the equation in both the manipulation process. First, when I am adjusting R4, at that time also both of them are getting disturbed. And when once again I am adjusting R1, once again both the equations are disturbed. So that means what? This is not the case. Now did you understand? Now did you understand?
Yes, sir.
Tell me. Okay, so now we are left with option C and option D. So once again, let me write both the equation for you. So this is option D now. So R1 R4 plus X1 X4 is equal to R2 R3 and X1 R4 is equal to X4 R1. So now check option C what it is said. First adjust R2. Okay, so R2 I need to adjust. So R2, is it present anywhere? No. So this is my first adjustment. and then you have to adjust R4. So now after this you are adjusting R4. Okay, so you are adjusting both the equation. So tell me, once you have adjusted this, then you are disturbing both the equation by doing what? By manipulating R4. So which one is more feasible? Option C or option D? Which one would you like to do? Option D. So that is your answer then. Okay, first adjust R4, then adjust R2. This was one of the best question you can see. Okay, very good question, because nothing is said, you have to do it like this. So did we understand now? Did we understand? Any doubt? So like this you have to do analytical explanation of all the options. So this was very good question. Okay, chalo. So measurement of capacitance we have to do. Before that, let us solve one more question. Chalo, let us solve this one. Tell me, can we solve this question or not? Or else it's okay. It's okay. What we will do, we will cover the theory part. Okay, theory part is left. So in the next 1.5 means half hour or 1 hour, what we will do, we will cover this theory part, and then I will leave this question as homework, so that in the next class you can solve this question and then Hello, am I audible?
Yes, sir.
Am I audible? You can see me.
Yes, sir.
This is shown. Connection status. It's very weak over here because it's raining. This is very bad service by Airtel. Okay, fine. Chalo. Till the time we don't have any issues, we can continue with the class. Okay. So if issue persists, then we will stop the session. My voice is clear. Hopefully, it's not breaking.
Yes, sir. Clear.
Okay, chalo. So what I was telling this that questions I will give it to you as homework rather than waiting for you guys to solve the question. So what we can do, we can finish the theory part because it's very simple. Okay, we are going to work on the same thing, means whatever we have studied up till now, same thing is going to continue. Only thing is that the bridge, the diagram of the bridges or the construction of bridges, it is going to change. Okay, so now we have studied about what measurement of inductance we have seen. Okay, so now we have to see measurement of capacitance. So how many of you can draw, means this is the capacitance that we draw in our circuit theory, we term it as C. Okay, this is your ideal capacitor. If you want to draw the practical capacitor, how many of you can draw? Can you draw the exact model of capacitor? Just draw it once. Just try. Tell me. Do we know this model? What are all these parameters? You don't know. Okay. So this C, basically it is over here. This R, this is actually R insulation. You never see a capacitor like this, which has plates. It's not like this. Basically, it is in a cylindrical shape, something like this. Your capacitor is enclosed. Okay. Medium, even inside this there are liquid or oil present which act as your dielectric. Okay, so this is basically the resistance of the insulation, which is right, and this insulation, it is very high, very high. Approximately you can tell it to be as infinite. Okay, next is what? Equivalent. This is known as ESL. What is ESL? Equivalent series inductance. Okay, equivalent series inductance. Can you tell me what is the value of this equivalent series inductance? Anyone? So this ESR is basically what? It is your equivalent series resistance. Okay. So basically this equivalent series inductance, it is usually in the range of nanohenry. Okay, nanohenry. So that is very, very small, 10 to the power minus 9. Whereas this equivalent series resistance, it is in your milliohm region. Milliohm region. Okay, it is in your milliohm region. So now basically if you want to approximate it, so you can draw this like this is your ESR and this is your capacitance. You can neglect this ESL and this insulation, it is present like this. You can approximate it as your open circuit. Okay, so this is how is your equivalent model of capacitor. Even usually we neglect this one also. Okay, we neglect this one also. At that time we might get something like this. Okay, any doubt in this up to this point? So this is known as leaky resistance. Why leaky? And this is known as lossy. See, whenever in parallel, if this R insulation is less than infinite, so what will happen if suppose current is flowing from here, I, so some amount of current will flow, very negligible amount of current will flow through this path. Okay, if this was infinite, this whole I would have flown through this capacitor, but as this is not means equal to infinite, some of the current it will leak over here. Let this be I dash. So the amount of current that is flowing through capacitor, it will be I minus I dash. So that is why it is called as leaky resistance. Why? Because it is leaking some of the current over here. And why this is called as lossy resistance? If suppose this current means if this resistance was not present. Okay, if this resistance was not present, look over here. If this ESR was not present, then the energy dissipated, means no energy will be dissipated. Energy stored by this capacitor, it would have been half CV square. No energy will be dissipated, only this much energy will be stored. But due to this resistance, what will happen? There will be a continuous loss of energy. It will be I square into whatever is the minimum or the minimal value of this resistance, let it be R. So there is continuous loss of energy. So that is why it is known as lossy resistance. So did we understand the difference between leaky and lossy? So leak always happens in parallel, loss always happens in your series. Any doubt in this? Okay, chalo. So next we have is, first is unmodified D-Shorty bridge. Okay, the most simplest bridge. Here you can see this C1 is unknown. Okay, so I should have actually told. So it's okay, we can even discuss this. So over here you can see ESR, equivalent series resistance. I have approximated it as 0 ohm, and your R insulation, I have approximated it as infinite. Okay, in unmodified D-Shorty bridge, this C1, it is basically your unknown capacitance value. Unknown. So if you want to do the analysis of this circuit, so let this be Z1, this be Z4, this be Z3, and this be Z2. So we know what at balance condition Z1 into Z4 equal to Z2 into Z3. So Z1 is 1 by J omega C1 into Z4 is R4 is equal to Z2. So 1 by J omega C2 into R3. J omega cancel. So 1 by C1 is equal to R3 by R4 into 1 by C2, or C1 is equal to R4 by R3 into C2. So this is the expression that we get. Okay. So now out of this R4, R3, C2, you can vary any one of the following. So usually we vary this resistance because we know capacitance, varying capacitance, it is expensive. Okay. Variable capacitors are expensive. Okay. So any doubt? Any doubt? Tell me. Okay. So let me ask you over here, what is the quality factor? Quality factor first. Quality factor of this capacitor. And next is power factor. Arey, what happened? Quality factor of this capacitor is 1 by omega R1 C1. You can see R1 is equal to 0. So this will be 1 by 0, which is infinite. So this is a infinite quality factor capacitor. Why? Because we have taken the ideal capacitor. In ideal capacitor, there is no resistive part present. You can see I have excluded the parallel part, means I have taken it as open circuit, and the series resistance part I have assumed it to be zero or short circuited. So that is why quality factor is infinite. What about power factor? What is the power factor of this element? Arey baap re baap. Now we cannot tell even what is power factor. Power factor is cos phi. Phi is what? Phi is your phi v minus phi I. Okay, so there is, means we know what in capacitor phase of the current leads by 90 degree. So if I take mod, so this will be always 90 degree. So cos phi will be what? It will be cos 90 degree. So power factor is 0 for an ideal element. Is it clear? Tell me. बताओ क्या हम पढ़े हैं? Nitish? I have told this in the class that power factor of an ideal element is always 0. Arey, now even we cannot tell this. Why power factor is 0? Because we know cos phi is equal to R by Z. Okay, in series circuit it is R by Z. So if I multiply both, means in the numerator and denominator, so you can see as R part is 0, so there will be no real power. Okay, real power will be 0. So that is why cos phi is 0, because there is no resistive part. Is it clear or not? Tell me. See, these are all logical things. Okay. So this is known as what? This is known as unmodified Desauty bridge. Okay, unmodified Desauty bridge. Now the next we have is what? We have modified Desauty bridge. Now what happens if suppose, means you can see basically this is ideal condition. So in ideal condition we are facing this problem that quality factor is infinite, power factor is 0. So what happens if suppose we don't have, means what I have assumed that your ESR is equal to what? Equivalent series resistance is 0 ohm and R insulation is equal to infinite. But here you can see, if suppose that is equal to 0, see R insulation is very, very high. You can never expect this to come down because insulation has very high resistance. So only expectation we have is from this equivalent series resistance. It is also very, very less, milliohm, but sometimes this can be even in the micro ohm region. So at that time, we have this provision of R1 in the circuit. We can vary this R1 so that this capacitance has some amount of resistance, and we know already this value of R1. Okay, so we can determine C1. But if by default, if there is some R1 present, if ESR is not equal to 0, then what we do? In this circuit, we set R1 is 0. So we can do this. So this R1 is present so that if ESR is equal to 0, at that time we can introduce R1 in the circuit. If R1 is not equal to 0, then we make this small R1 as 0. Tell me, did you understand the purpose of this small R1? Did we understand?
So once again, sir,
See, once again I will explain. If suppose we had this bridge, so here in this bridge you can see ESR is 0. We have no option. Okay, we have no option. Quality factor is coming out to be infinite. There is no way I can measure the quality factor. Now why is this happening? Because the resistance which is present over here, this ESR, it is very negligible. Okay, it is very negligible. But if I want to calculate, suppose in this only I want to calculate quality factor. So what I can do, I can induce one external resistance small R1 at this point. Now this value of R1 already I know. Now with the help of this R1, what I can do, I can make an approximate judgment about the quality factor of this coil, or even I can do certain other manipulation also. So this R1 basically I am introducing. Now this R1 will not be required when I have this significant ESR. If I have a significant ESR which is denoted by R1, then what I will do to this small R1, I will simply make it 0. So this is what is your modified Desauty bridge, where we have provision actually for this small R1. Now is it clear? Tell me, Shishir.
yes, sir, clear.
Okay. So same way, once again, we are going to do the analysis over here. Let this be Z1, Z2, Z3, Z4. So here R1 and C1 both are unknown. This small R1 is known. This is known. These two are unknown. Okay. So now for balance condition, Z1 into Z4 is equal to Z3 into Z2. So Z1 is equal to R1 plus small r1 plus 1 by j omega C1 into Z4 is R4 is equal to Z3 is R3 into R2 plus small r2 plus 1 by j omega C2. Now can anyone tell me why do we have this R2 over here? Why do we have this R2? So you are going to see, okay, don't worry. Okay, so what we can do now, so R1 plus small r1 into R4 is equal to R3, R2 plus R2, and over here we have what? R4 by C1 is equal to R3 by C2. Okay, so C1 is equal to R4 by R3 into C2. See, once again we are getting the last equation only. Okay, there is no change. You can see there is no change that we are getting. Okay, but what about this one, R1? So this is actually R1 is equal to R3 R2 plus small r2 by R4 minus R1. Okay, tell me, up to this point is everything clear? Is everything clear? Now why do we have this R2 then? R2, tell me. Why? So what is the change? See, basically, if you can see over here, okay, if you see, if this capacitor also didn't have resistance, then once again I cannot calculate quality factor. I cannot calculate quality factor. So this is why this R2 is introduced over here, so that I can manipulate the circuit to calculate the quality factor of the coil. So this R2 is induced in the circuit, so that if sometimes this capital R2 is 0 due to the manufacturing process, so at that time I can introduce this smaller R2 so that I can manipulate this circuit. Tell me, now is it clear? Why do we have small R2? Tell me, is it clear?
Yes, sir. So for both the C1 and C2, we have R1 and R2 in their branches.
What? I couldn't get you. What you are telling?
Since in the C1 capacitance 1, we are introducing R1s if we haven't been provided R1, capital R1. And in the
Pardon?
C2, we have to,
See,
sir, for
basically I
the,
have introduced this R1 to nullify
because,
this effect.
yes, sir.
है ना? So to calculate, basically to do what? To make this capacitor switch from ideal side to practical side. Okay, because we can measure practical capacitance value, we cannot measure ideal capacitance. See, here also the equations are same like before, but the capacitor is not acting as what? It is not acting as your ideal capacitor. See, C1 value, whatever value we were getting in the last time also, we are getting the same thing. But the thing is that here this capacitor is not ideal. So I can calculate quality factor of this capacitor. Okay, I can calculate it. It will be what? 1 by omega R1 C1. Okay. So now this R1 I have already over here. This C1 is also present. So I can calculate it. But if somehow this R2 was equal, sorry, this R2 was 0. If R2 was 0, then also once again you are going to see that, see, I will show you. I will show you. Chalo. So where I can show quality factor is equal to 1 by omega into R1 C1. So R1 is R3 by R4 into R2 plus R2 minus R1 into C1. So C1 is R4, R3, C2. Now if suppose what is happening, that this capacitance value, it is ideal. Once again I am telling this capacitor is ideal. Now if this is ideal, what will happen? Capital R2 is equal to 0. Capital R2 will be equal to 0. So this will not be present over here anymore. Okay. Now if we don't have this R2, so what will happen? If we don't have this R2, then this will not be also present. Okay. So can we have a negative value of quality factor? Tell me now. Can we have negative quality factor? Now this is highly illogical. So that is why we have this R2 present over here. Is it clear now? Is it clear? Understood? Chalo, badhiya. So next is what we have. We have is sharing bridge. Okay, what is the sharing bridge? So sharing bridge is also used for what? It is used for your measurement of capacitance only. Only thing is that your response means what? This balancing is very faster compared to Desauty bridge or modified Desauty bridge. Okay, modified Desauty bridge or Desauty bridge, your calculations are going to be faster. So let us do the same thing over here also. So let this be Z1, this be Z3, this be Z2, this be Z4. Okay. So now you can see at balance condition Z1 into Z4 is equal to Z2 into Z3. So Z1 is equal to R1 plus 1 by J omega C1 into Z4 is what? So directly I am going to write R4 divided by 1 plus J omega R4 C4, or else it's okay. Calculation will be difficult or what? No, it will be okay. Yeah, it's okay. Chalo. Into is equal to Z2. So that is 1 by J omega C2 into R3. So if I solve this, this is going to be what? R1 minus J by omega C1 is equal to R3 by R4 1 plus J omega R4 C4 J omega C2, which is equal to R1 is equal to what? So R1 will be equal to, so directly I am writing R4 C4 by C2 into R3 by R4. This is your R1, and from here what I can write, 1 by omega C1 is equal to R3 R4 into 1 by omega C2. So omega gets cancelled, R4 cancels. So we have over here R1 is equal to C4 by C2 into R3, and C1 is equal to R4 by R3 into C2. See, now we can very easily even calculate quality factor also. Previously you can see quality factor was what? R3, what we had written, sorry. So this was R2 plus R2 minus R1. There were a lot of terms over here. But now if you check over here, quality factor, calculation of quality factor is what? 1 by omega R1 C1. So if you check over here, so 1 by omega into R1 is C4 by C2 into R3, and this is equal to R4 by R3 into C2. So C2 cancel, R3 cancel. So quality factor is equal to what? 1 by omega R4 C4. You can see even calculation of quality factor is simpler compared to this one. Okay, and even the response is faster compared to modified Desauty bridge. Tell me, is this clear? So this is the concept of sharing bridge. Okay, is it clear? Any doubt? So note it down quickly. Then we have this two thing, Wagner device and Wayne's bridge. So this thing we are going to do in the next class only. It's okay. Okay, we are just going to see this measurement of relative permittivity using sharing bridge. Okay, this thing we are going to see. So quickly note it down. Means this has never been asked, measurement of relative permittivity using sharing bridge, but from last 4 years I am still teaching. Someday it might be asked. To which batch I don't know, but if it is asked then you should be knowing this. Noted? So now what we are going to do, with the help of sharing bridge, we are going to calculate the relative permittivity of this medium. Okay, this is the medium we have, this green color. This is the medium that we have. Okay. So if suppose I want to calculate the relative permittivity of this medium, so how are we going to do this using sharing bridge? That only we are going to see. So now if suppose I have to calculate the equivalent capacitance. So here you can see, here we have air, here we have medium. So equivalent capacitance is equal to what? Basically, if this is C air, see I have even noted. So it is C air series with C equivalent, capacitance with dielectric medium. Okay, dielectric medium. See, is it clear or not? Tell me. Both of them are in series. Any doubt? Fine. If it is in series, means okay. So I shouldn't have written it. This is actually looking like parallel. Okay. So I should write it like C air is in series with C dielectric. So this can be written as, we know what, C air into C DIE divided by C air plus C DIE. Tell me, is it clear? Is it clear? So now C air, I can write it as epsilon naught A by D. So here this is D. What about C dielectric? I can write it as epsilon naught into epsilon naught R A by T, because this is what? This is the distance between these two plates. Tell me, up to this point, is it clear? Okay, fine. So next, once again, let us put this. C equivalent is equal to epsilon naught. See, area of the plates are same for this two. Okay. Epsilon naught epsilon R A by T divided by epsilon naught A D plus epsilon naught epsilon R A by T. So from here, let this be like this only, epsilon naught A by D into epsilon naught epsilon R A by T divided by, let me take this as common, epsilon naught A by D common, 1 plus, sorry, I cannot take D common, epsilon naught A common, so this will be 1 by D plus epsilon R by T. So this cancels. Okay, now let me take LCM and solve it. So this is what? Epsilon naught epsilon R A by dt, and this will be T plus epsilon R into D divided by dt. So dt cancels. So what I get? I get epsilon naught epsilon R A by T 1 plus epsilon R D. First note up to this point. Noted? Tell me. So this is what? This is C equivalent. Let me mark this as C equivalent 1. Okay. C equivalent 1 is what? When the dielectric medium is present. So what we get? C equivalent 1 is the capacitance when this medium is present. It is epsilon naught epsilon R A divided by T plus epsilon R D. Tell me, is this clear? Okay. So this actually, this C equivalent, it is placed over here. Okay. It is placed over here. I place it over here. Okay. Fine. Now what I do, I will remove this medium. Okay. I remove this medium. See, when this, see once again, look, when this medium was present, if suppose this is my detector, let this be 0, this be some negative value, or I can even take it as voltmeter. Let this be 1 voltmeter only. So let this be 0, this be 1, this be 2. Okay. So when your medium dielectric was present, this voltmeter, it was indicating somewhere over here. Let us assume it was indicating this much. This was 1.8. Okay. Is it clear? Tell me. So this is actually the indication when dielectric was present in this capacitance. Now what I will do, I will remove this dielectric medium. Okay, I will remove this dielectric medium. So what might happen? What will happen? Will your capacitance increase or decrease? Will your capacitance increase or decrease?
Decrease.
If I, huh? Yes,
Decrease.
your capacitance value will decrease. Okay, your capacitance value will decrease. Hello, let us do it in the next page. So this was dt. This much part is d and this is t. Okay. So your capacitance value was what? C equivalent 1 was epsilon naught epsilon r a d divided by epsilon r d. Okay, so the moment you remove this epsilon r, means this medium is removed, your capacitance value, let it be denoted as C equivalent 1 dash. This is actually less than C equivalent 1. Okay, now your meter is basically indicating, it was previously at this point. Now as your capacitance value has decreased, this meter will also indicate a lower value. Now what I want to do, once again, basically this capacitor, I can actually vary the distance between the plate. I can vary this distance between the plate. Now if I want to increase the capacitance value, what I can do? Either we know what C is equal to epsilon naught A by D. Now this is for any capacitor I am talking, any capacitor, not at this particular place. Don't consider it for this particular case. For any capacitor, a random capacitor I am talking about. So this is your capacitor which has area A and distance D. If I want to increase the value of capacitance, what I can do? Either I can increase the area, or what I can do? Decrease this distance between the plate. Now area I cannot do anything. Okay, how can you change the area of the plate? What you can do? You can manipulate this distance. Similarly over here, what I do? I will be manipulating the distance between the plate. So previously it was d plus t. You can see d plus t. Now what I will do? I will decrease the distance between the plate such that I move it from x position. Okay, x distance I move it. So now basically what is this much distance? It is d plus t minus x. Tell me, have you understood this or not? Please tell me. Did we understand? Nitish, Shishir, both of
Yes,
you?
sir.
Okay, fine. So now what will be C equivalent to? Now for this C equivalent to, what happens? This pointer, it moves from this position once again back to this position. Okay, when we had dielectric present. So I am basically manipulating the distance so that we increase the capacitance and go to the previous value. So when that happens, we are going to write C equivalent is equal to epsilon naught A divided by D plus T minus X. Now at this particular time, equation 1 and equation 2 are same. Why? Because your Meter is indicating the same value. That means the capacitance values are now same. So equate this two. So what we get? Epsilon naught epsilon r A divided by D plus epsilon r D is equal to epsilon naught A D plus T minus X. So what we get? Acha, so we got over here epsilon r D plus T minus X is equal to D plus, okay, so I can take D common. Last time I was getting this. Okay, so there was T na, so that is what I was thinking. This is T. So we get what? D plus T minus X is equal to, sorry, into epsilon r is equal to T plus epsilon r D. Okay, so let me bring this over this side. So epsilon r common, D plus T minus X minus D is equal to T. So D cancel. Epsilon r is equal to T divided by T minus X. We get over here. So this is the value of what? This is the value of epsilon r, which is equal to T divided by T minus X. So we actually know the value of this T. Okay, value of T we already know. Okay, and this X we calculate it using what? We calculate it with the help of this variable capacitance. We already know the value. So with the help of this bridge, sharing bridge, we can even calculate the relative permittivity of the medium. Tell me, is it clear? So this is the formula where T is actually what? T is the thickness of medium, and what is X? X is the displacement of plate. After medium is removed. Any doubt? Any doubt?
Sir, actually, why especially through steering bridge only we can calculate this? Like, given only we are manipulating the capacitance and the distance between plates. So, why only sharing bridge is used to calculate?
See, with the help of sharing bridge, I told you. Lastly, we have studied what? We have studied two bridges. One of them was unmodified Desauty, another was Desauty. So in Desauty and unmodified Desauty, the problem was that basically the response was slower. Response was slower because there are lot of resistance involved over here. Whereas in your sharing bridge, we don't have that much resistance involved. Directly with the help of this, if we manipulate this R4 and C4, we can directly get this value of R1 and C1. So that is why we are using sharing bridge. Tell me, is it clear now?
Okay, sir, yes.
Fine. So then we are left with just Wagner device, okay, and Wayne's bridge. Wayne's bridge is used for measurement of frequency. We are left with this one, these two bridges. Wagner device is not in our syllabus, okay, means it is written, just one line is written. So we will just study the basics of Wagner device, why it is used, and then we have some questions. So these questions you can now solve, okay. I want you to solve all these questions. I will be sending you the slides. So in between, I might keep one class. Okay, I might keep one class. So let me think when, because the last week we couldn't have one class. So let me keep one class this week. So let me see, because now from 550 to 750, I think Prashant sir is taking your network class. So I have to see which day he is not taking, and I am also available. At that day, I will take your class. Okay. Any doubt? So I will